we are looking at mutually and non-mutually exclusive events. We're going to talk about what that means. Okay, so first off, you write down the definition of what a mutually exclusive event is. Events that have different attributes and cannot occur simultaneously. So an example of that is this Venn diagram here, and we have event A and event B, and they're mutually exclusive because they don't have any intersection. Now, on the next slide, you'll see an example of a non-mutually exclusive event, and that helps us understand what a mutually exclusive event is. And that's different events that can happen at the same time. So here we have an intersection, and we have two events, A and B, and they're different events, but they have an intersection where they can occur at the same time. Now, an example of that is, this is a deck of cards in case it's not clear to someone in the class, where there's a bunch of cards and there's an ace of hearts, a two of hearts, three of diamonds, three of spades. These are spades, these are clovers, and these go from ace all the way to 10. Ace represents 1, 2 to 10, and then there's jack, queen, and king. So for this class, you have to become a little bit familiar with a deck of cards because we use it for counting exercises quite a bit. Now, how many cards are clubs? Now, these are clubs, also called clovers. There's about 13 of them, and there's 13 of each suit, these are called. And how many cards are spades? So these are spades, and as you can see, there's no intersection. Okay, so create a Venn diagram for the list of clubs and spades. Well, here's clubs, here's spades, and as you can see, they are mutually exclusive. Okay, these are all the clubs in the deck, these are all the spades in the deck, and furthermore, this gray area here is the entire sample space. So this is every other card, so all diamonds, and hearts are in here. Okay, so how many cards are there in the Venn diagram? Well, there were 13 spades, 13 clubs, and the number of clubs and spades were 26. But total, are in the Venn diagram, well, inside this Venn diagram, it is 26. Okay? Counting cards. So how many cards are diamonds and how many cards are face cards? Now, what's a face card? Jack, queen, and king are face cards. Okay? So how many of them are diamonds? Well, if we look, and we're going to create a Venn diagram for that. So as you can see, our diamonds are here, and our face cards are over here. But there's some intersection, so it's not mutually exclusive. So they're different events. Face cards is an event, and diamond is an event, but they can happen simultaneously, and therefore it's non-mutually exclusive. So all the diamonds in the deck, all the face cards in the deck are green, and all the cards in the entire sample space is represented in gray. So how many cards are in the Venn diagram? Well, we have 13 diamonds, 12 face cards, right? And the number of diamond face cards is 3. So essentially, if this was A and this was B, if we just added n of A plus n of B, we'd end up getting 13 plus 12, which is 25. But we would have double counted these 3 that were in here, right? So we subtract the double counting. So if we subtract what we double counted, then we counted once. And so the answer is 22. And essentially how this works is, if there was 12 here, and 12 face cards and 13 here, well then essentially this 13 would be this whole thing, 10 plus 3. And this 12 would be 3 plus 9, right? Which is 12. Now, if we added 12 plus 13, that would have counted this 3 2 times, right? 1 for here, 12, and 1 for here. So we have to subtract the 3 one time. Okay, so let's work with examples. A picnic basket contains 3 ham, 2 turkey, 1 chicken, and 4 egg salad sandwiches. What is the probability of randomly choosing either a ham or an egg salad sandwich? Use a Venn diagram to illustrate outcomes. So what is the probability of randomly choosing either a ham or an egg salad sandwich? Well, they are non-mutually exclusive events, right? So this is ham. There's 3. Actually, I think I do it here. So that's ham. There's 3 of them. And that's egg salad. You cannot have an egg salad ham sandwich in this scenario. So what are we doing? So what is the probability? So there are 7 favorable outcomes. What's the probability of getting ham or that? Well, it's 1, 2, 3, 4, 5, 6, 7. It's n of egg or ham. Well, that's 7. And then there's 10 total outcomes, right? Including these 3. So P of H or E is equal to 7 out of 10, which is 70%. Okay, we could also use probabilities where we calculate that, there's 7 out of 10 favorable outcomes, but the probability of ham right there is 3 over 10, and the probability of eggs, that's 4 over 10. So if we add them up, we'll end up getting 7 over 10, which is also 70%. Okay, and that brings us to the additive principle. So P of A or B is equal to number of times n A or B exists over ns, the whole sample space. And this only applies for mutually exclusive events. Okay, the probability of either of 2 mutually exclusive events are A or B is P of A or B equals P of A plus P of B. Now, this is just a proof right here, right? NA plus NB, the number of times A occurs plus the number of times B occurs over N of S. And mathematically, we can just separate this, right? And that's how we got that. And that's the definition of P of A. And that's the definition of P of B. Okay? And that only works for mutually exclusive events. So we talked about this example. Find the probability of randomly selecting a diamond or a face card. So n of D, we called it D for diamond, is 13, and n of F is 12. Now, obviously, we can't just add n of D plus n of F because we'll overcount, okay? We'll overcount and it'll be 25, but if we count them fully, it's 1, 2, 3, 4, basically 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, and like we said, we double counted this, so total is actually 22, but we double counted this, so we subtract 3. So if we count the number of outcomes, there are only 22. N of D plus N of F counts both sets twice, so what do we have to do? Well, what is N of D or F? Well, we already did that already, right? And that brings us to this principle. Principle of inclusion or exclusion. If A and B are non-mutually exclusive events, then the total number of favorable outcomes is NA or B is equal to N of A, count it, N of B, minus the intersection of it, one time. So that's equal to N of D plus N of F minus N of D and F. And that's what we did earlier too, 13 plus 12 minus 3. All divided by N of S, which is 52, and that's 22 over 52. So it's equal to 42% chance of selecting a diamond or face card from a deck of cards. Okay, reset to example 3. In a room with 30 students, 10 play basketball, 15 play volleyball. So I have 30 students, 10 play basketball, 15 play volleyball. Okay, if 7 students play both sports, what is the probability that a student chosen at random plays basketball or volleyball? So apply the principle of inclusion or exclusion because, well, let's see. Did we draw a Venn diagram? We can draw a Venn diagram as well. So we have 10 playing basketball, N of B equals 10, and N of V is equal to 15. So we have something. If this is B, 10 total, but 7 play both, there's 7 in the middle, that means there's only 3 left there. And if volleyball, there's 15 total, well, we have 8 who only play volleyball and 7, and 8 plus 7 is 15. Okay, so but if we apply, we don't have to draw a Venn diagram every time. If we just apply this, N of V or B, how many of them play both? Well, it's actually 3 plus 7 plus 8. We're going to end up getting 18. So N of V, volleyball is 15, plus N of B, which is 10, minus 7. So N of V, 15, N of B, 10. N of V and B is 7. So we end up getting, we do the math, 15 plus 10 minus 7 is equal to 18. So probability of V or B is equal to, count the number of people that play volleyball or basketball divided by NS, and you get 18 divided by 30, which is what we got here anyway. 18 divided by 30, which is 60%. And that's the answer. Okay, so you'll say, now that's pretty much it. The probability of non-mutually exclusive, that means when there's intersection, non-mutually exclusive events. The probability of either of two mutually exclusive events, A or B is, P of A or B, is the probability of A, add the probability of B, subtract the probability of them both occurring at the same time. Okay, so playing tokens and their characters for an role-playing game, for an RPG, is shown below. So let's see, I don't know what this really means. It's if you're human and a knight, princess, you get a token. Anyway, if Hozo is randomly assigned a playing token, what is the probability that it will either be an animal or a supernatural creature? Oh, I see. So this is the characters. And it can either be a human, animal, supernatural, it can fly, and it can cast spells. So how many animals are there? There's 1, 2, 3, 4, 5, 6, 7, 8. I think N of S means 8, so N of S is 8. And then what's the probability that, well, it is an animal? Well, it can be an animal and supernatural. Right there, a unicorn is an animal and supernatural, so it's non-mutually exclusive. So the number of animals, there's 1, 2, 3, 4 of them are animals, and then 4 of them are supernatural. But I can only be a dragon, hawk, knight, lion, princess, etc. Let's clear this page. So how many are both? How many are supernatural and animals? So that's 1, and that's 2. So P of animal is 4 over 8. The probability of it being supernatural is also 4 out of 8. And the probability of it being both is 2 out of 8. So if we use this principle, probability of supernatural or animal, we add this plus that and take away that. So we add this, add that, and take away that. It becomes 6 out of 8. And if you think about it, let's take a look at this. Which animals are both? We got or either 1, 2, 3, 4, 5, and 6. So the probability is 6 out of 8 that I'll get one or the other. Right? It's a really easy question, but we're kind of making it complicated with math, but it's important to understand the math. Okay, so the probability that it's supernatural or an animal is 75%. And these working questions will be done in a separate video.